Okay, so Jim and I are going to talk about a system that we have for building agents within. It's called Soar, and we use a robot and environment simulator called AI2-THOR. It comes from the Allen Institute for AI. It's built within Unity, so it includes a physics simulator, and it's geared towards doing AI research. It actually has two pieces, I'm actually going to skip ahead just a second. It's got, yeah, sorry about that. It has, there's a Python library, and that's sort of where the developer, the client using AI2-THOR is expected to write their code, and that communicates over HTTP with an executable that it's running the Unity engine. So it's got the physics simulation in there, and it's got all the rendering and everything in there. I'm going to back up one more time. So this is what the Python code looks like. It's fairly simple. You import a controller, you create the controller with a few initialization parameters. So you can select from a bunch of scenes. They have kitchens, bathrooms, bedrooms, and one other, probably living rooms or something. And then you can select, so the width and the height is just, you get a window that pops up and shows you what the robot is seeing at any given time. So that's how you initialize it. Then after that, you do steps with the controller. So what that means is you pass an action in. So rotate left means the robot will turn 90 degrees. You can actually specify how many degrees to turn. There's move ahead. There are update. There are more complex, thank you, actions which take arguments. So for example, you can open and close the microwave, you can pick up an object, you can turn the light switch on and off and so forth. And in this case, I think I'm putting a potato into the microwave. I'm already holding the potato, so you don't specify the potato here. And then we're closing the microwave because we're about to cook it. And the other thing that I did not show is once you pass that action to AI2-THOR, please update. You pass that action to AI2-THOR, the physics engine runs until quiescence, meaning, if there was a ball rolling away or if there's some glass that shattered or something, all of the physics simulation is run to completion until everything stops moving, and then it sends back a new world state. You get this event back, and then you kind of have to go data diving into that to get the full state of the scene. So there's mostly what we use is there's a list of objects. And if I printed this out, this would probably give me something like Apple 1. It's a super long ID. It has these vertical bars within it, and you'll see we have to change these for Soar because they're not very useful. If you know, Soar uses vertical bars for quoting. Where are we now? So this moving kind of, oh, come on. I think this might actually fix itself in a second. Right. Well,
I think it'll work fine when I show some demos.
So John's going to show up more later, but the robot moves around in the kitchen, picks up a potato, puts it in the microwave, pulls it out again. When it goes to pull the potato out of the microwave, the color of the potato is different because it's cooked. And so I don't know how to pause this actually, but main thing to notice here is one, it does look pretty nice, but two, all of the actions that we take are kind of symbolic. So there's no, the robot isn't reaching up and grasping the microwave handle and pulling it open. It's more like a symbolic level action. We say open the microwave and the microwave is open. And we also have available, we can use third-party cameras as well. So for different demos, so I just call this a security camera, and then you can watch the robot move around the kitchen and perform its actions. So I showed you that architecture. More specifically, it's using HTTP. Yeah. Okay. So we kind of have a big Python wrapper with extra logic in it for our use case that runs alongside the AI2-THOR Python. So I showed you before with AI2-THOR, there is the the cycle where you send a command and then you get back the world state. Since we're putting Soar in the loop, we have Python in the middle. And what happens is we give Soar the current world state on its input link and also on SVS. Soar runs some decision cycles and updates the output link. And if that output link says, I need you to move forward, or I need you to open the microwave, or whatever it might be, then that gets passed through the Python processor, goes to AI2-THOR, world state is updated, passed back to Soar, and so on. That is the event loop that we have in this program. Yep. Okay. So more technically speaking, so we have 4 threads. There's the main thread where we launch. There's Soar thread, the source thread, which is where the entire event loop runs. The AI2-THOR Python library has its own thread, which maintains a message queue. So you send the actions that you want the robot to perform to that message queue running in that thread, and that manages the HTTP connection to the AI2-THOR process. So these are all of the threads that we have running. It does make debugging a little bit difficult sometimes, but we have been able to we can actually do full debugging within Unity to step through the C# code while we're also stepping through the Python code, but certain event handlers, unfortunately, we can't debug. I'm going to skip that. So one kind of interesting gotcha with AI2-THOR is that it has multiple APIs. So Manipula-THOR is the one where if you're really interested in controlling the 6 degrees of the robot arm and having it specifically grasp something, you could use that. For our research, we're not so interested in that. We're more interested in planning and such, and interactions with objects and all that. So we use the AI2-THOR API, and that provides symbolic actions as well as scenes that have a lot of interaction with them. So it's got the toaster, it's got the stove and the microwave, and they look really nice because they're designed by a professional architect. Some of the assumptions that are kind of built into the system. Wow. Sorry, some of the assumptions that are built into the system right now, mostly because of AI2-THOR, are one, objects are identified for you. They have permanent identifiers associated with them. So we don't have to kind of parse out camera data and decide where objects are in the scene. We don't do the motor control, as I said, and AI2-THOR also gives you a complete view of the scene. And tells you which spaces in the scene are open in kind of like in a grid. So you can use that to navigate the areas of the scene. And AI2-THOR has, I think, about 200 objects. Each one is specified as having a particular number of affordances. So like, I think this is alarm clock. Okay, you can pick up the alarm clock. This one here is an apple. The apple you can pick up and you can slice and so on. All of the objects in the scene have these affordances associated with them. Our Python application uses PySoarlib, which was written by Aaron Minninger a few years back. It's actually more of a framework for creating Soar applications. It wraps the Python SML bindings and manages for you registering handlers. It manages doing I/O with Soar, the agent and the kernel lifetime, and also simplifies configuration. We have extended the original version that Aaron wrote, and it is available at this URL on GitHub. And for the agent, there's some basic configuration, including like how far can the robot see? Where's your agent source? Where's your semantic memory database, and so on. So I'm going to show you, I'm going to skip ahead one. So some of the information that we pass through related to objects, that is not what I wanted, are, for example, the material. So if you want the robot to pick up all of the glass to recycle, then you can say, grab all the glass things, because we have information about the material from AI2-THOR. And then mostly lots of Boolean state variables that come through from AI2-THOR. So is the apple sliced, or is it still whole? Is the dish dirty, or is it clean? Is the cup broken, or is it still in one piece? And we also pass everything onto the SVS, into SVS, which is really annoying to look at this way, much better in the SVS viewer. So here's the robot with this is just sort of a symbol of which way the camera is pointing at a given time. That's a fridge. This is the counter here. If we go into mesh mode, you can kind of see that there are a lot of hidden things in here. So inside of the cabinets, you have got a plate, you've got a cup. Inside of the fridge, there's an egg. So there's quite a bit for the agent to explore the scene and find. Last thing before I get to Jim's part, I-THOR doesn't have any conception of time. You can't say move time forward this amount and tell me the state of the scene after that. So we have to for complex timers such as cooking things in the microwave or on the stove, we have to model all of that in Python. That we do it's configurable in this way. We say there's a certain number of milliseconds that pass for each decision cycle. Each action takes a certain amount of time. And we, if something is cooking on the stove or in the toaster, etc., then we accumulate cook energy. So it's just kind of counters that go up over time. And we allow the agent to mess up and burn the toast if you leave it in there too long. I'm going to turn the time over to Jim for the rest of it. That's all right, Jim. I skipped ahead a little bit, but getting out of time here.
Okay. Oh, yeah. So, as I was mentioned earlier, AI2-THOR is based on Unity, and Unity is a well-known game engine. Previous place I worked with, they used the other big game engine, which is Unreal. I think they're similar, and they're both used to create games with detailed simulations. I was gonna say that AI2-THOR is I'm gonna say can I just say air quotes game? You know,
Sure.
It's a game, but it's a little bit different than regular games in that it has both lower fidelity and higher fidelity in certain ways compared to typical games. I think it's higher fidelity in the sense that almost everything in the game is interactable. There really isn't just kind of cutscenes or something like that. It's lower fidelity in that the interaction with some of the objects isn't as fleshed out in all circumstances. So what's been done to try to expand the game is to add objects. You're adding items, and you're also sort of adding interactions with the items. And been interesting to try to understand this process.
Just push right. Next one. It'll get there.
This isn't
Yeah.
what I was expecting.
You go too far?
Maybe,
Left one, maybe.
yeah, okay, just when this clears, just hold on to the same image. This is an image of the robot kind of looking to the left towards the sink, just kind of keep that in mind. For adding objects, the way Unity is built is everything's done with a bunch of different layers. You have layers to represent the artwork, which is kind of the physical view of the object. You have boundaries, which tells Unity, how it can be set on a table. It's the boundary of what it's touching and stuff like that. And you have receptacle boundaries, which tells you if it's something you can put something in, that gives you the boundaries of where those things can go. And then there's action specific components that can reference the existing scripts, whether something can be cooked or cleaned or opened and stuff like that. Let me just get to this picture. This is an example of a mesh, which is basically of the mug. It's just the artwork of the mug, and these can be obtained for either free or very low cost from different websites. And if you want to precisely put the collision for the object, you can base it on the mesh. Oops, that's too far. There you go. Yeah, it's a collision layer. Tell the reason there's different ways of collision, it has to do with the speed of the operation and how quickly you want the thing to run. And that really isn't a concern for this system, but if you want to have the mesh precisely map where the artwork is, you can create the collision layer based on the mesh layer. Otherwise, you can just use simple shapes. You can make a cylinder, and if you really want to, if you're concerned about the mug handle, you can add like a little rectangle onto it to make a collision layer that way. It's a nice furniture. Yeah, there's this other issue with visibility. This took me a little while to figure out, but something's considered visible if it's close enough, if it's in the view of the robot and it's close enough to pick up. And the way this is done has to do with a raycast operation. That's part of the physics aspect of Unity. Unity is basically a system where you can produce and place 3D objects plus physics. So you can add gravity, you can do all these other things like sunset. If you drop something, it'll fall and it might roll a bit. So for something to be considered visible, you have to a ray is cast from the robot, and it hits one of the visible points which are defined on the objects, and then it has to go a little bit further to hit a collision. So all those little balls are visible points on different objects. The mug has a whole bunch around it, and those need to be set up so that something can be visible.
Jim, we're running late.
Oh, okay. Okay, I'm shooting up. So this is the last image, and it's just showing all the blue lines are successful interactions with the visible points of different objects. And this is the just from the image before, this is the robot looking to that direction. They have a limited length of place where they can look, and if they can hit it, then it's considered visible and they can interact with it. And that can be set too. So I want to get to the
I think we can probably just.
nugget symbols there if you want. Okay.
Right, thanks. Sure.